Assalamu alaikum wa rahmatullahi wa barakatuh. Today we're going to start a new topic, which is lecture number 6. The new topic is time varying electromagnetic waves. In previous part, we talked about static magnetic field. In previous course 303, we talked about electrostatic field. And in these two cases, we have nothing changing with time. Either we have a stationary charges for electrostatic, or we have steady state current for magnetostatic. So this is called electromagnetic fields. Now we're gonna take an introduction, or like one step towards electromagnetic waves. And to do this transition, we're gonna like analyze and study a number of cases where the time varying is affecting the behavior of electric and magnetic fields. So let's start by a quick review for the postulates or the laws that are governing the static cases. For electrostatic, we have curl of E equals 0, divergence of D equal rho. For linear medium, we have D equal epsilon E. And just a quick reminder about the meaning of curl of E equals 0. This is the conservation of the electric field, or like uniqueness of vector potential, the uniqueness of voltage potential or electric potential for any point, which means that if we circulate along any closed path and integrated E dot dl along this path from one point to itself, the potential difference will equal 0. Divergence of D equal rho is the Gauss's law, which is stating that the total outflux field from any closed surface equals the total free charge enclosed by this surface. For magnetostatic fields, we have divergence of B equals 0, which is the conservation of the magnetic field, which means physically that the magnetic field lines are closed and the magnetic sources are like coupled. They are always dipoles of north pole and south pole. The second postulate is Ampere's law, which is stating that if we have like any closed path and you integrated H dot dl along this path, it will equal the total current penetrating this surface. So this is Ampere's law, and we had many applications on this. Those relations, as I said, are good for explaining the static cases, but those relations fail to describe the observations in case of time varying sources. When something is changing with time, this laws or this mathematical model doesn't give an explanation. As we talked before, that the scientists observe something, they study it, then start to think about a mathematical model to describe it, a mathematical model to express the relationship of what they observed. So experimentally, it had been shown that for time varying electric field, there is a relationship and interdependence with magnetic fields. So the current mathematical model that we just discussed here doesn't give this interdependence or interaction between electric field and magnetic field, nor the time varying dependency. So one of the observations that had led to this time varying study is Faraday's law, where he discovered that there will be current induced in a loop if this loop exists in a time varying magnetic field. So let us assume that we have any kind of loop rectangular loop in this case, and this rectangular loop exists in a magnetic field that is varying with time. The observation is that there will be some current I induced in this loop because of this time varying magnetic field. And the relationship between those two quantities is expressed here in this differential form, curl of E equal minus partial B partial T. And note that this relation is inconsistent with the static case, which means if there is no time dependence, the right hand side will be 0, which is the static case. So this expression in differential form also can be written in integral form, which is E dot dl, and this is called electromotive force or EMF. E dot dl across this path, closed contour, equal the time variation of the flux penetrating this surface defined by the contour, and this is called Faraday's law of electromagnetic induction. So let us have an example about Faraday's law. The example goes like this: a circular loop of n turns of conducting wire lies in the XY plane with its center at the origin. There is a magnetic field specified by this expression. The radius of the circular loop is B, and the angular frequency of the field is omega. We would like to find the EMF induced in the loop. At this point, I would advise you to pause the video and try to solve this example by yourself. All what you need is written here in this slide. You need to apply the Faraday's law and find the EMF. EMF is E dot dl. So I advise you to try solving this example by yourself. Pause the video now and try solving it yourself. Now I hope you are back from your trial to solve this example by yourself, and let us apply together the Faraday's law. So the EMF, as I said, is E dot dl across this contour, and it's equal to negative the integration of partial B partial T dot ds integrated over the surface area bounded by the contour. So for the differentiation, we just differentiate the expression for B. It will give us this expression. Then we need to find the expression for ds. If you remember that, for ds in this case, we just do like something like this. So this arc equal r d phi, and this edge equal dr. This is the area of this section here, equal r d phi multiplied by dr. Here's the expression for B is just dependent on r, so there is no dependency on phi, which means that we have a phi symmetry. So the field is constant with phi, so that we can integrate over this ring. So the field across the whole ring here is constant. Sorry for my drawing with the mouse. It's not that good, but anyway, I hope this is explaining what we are integrating. The area of this ring equal 2 pi r, which is the length of the ring, multiplied by dr, which is the thickness of the ring, and we are integrating from 0 to B. So this is how to come up with the expression of, let me bring, okay, where is my, sorry for that, okay. So we need to run to execute this expression, we take all the components that are independent of R outside of the integration, and we do the integration. This integration can be performed using the integration by part. The law of the integration by part is here. You need to review it and work out the integration yourself to come up to this expression, which is EMF, the electric motive force or electromotive force along this loop, and find out its expression.